We're going to continue along with linear regression today, and we are going to talk about another way to find the regression equation, and then we're also going to talk about something called a residual. So essentially, when you come up with your equation for the line of best fit, your line is not going to pass through every single number on your scatter plot. And so because of this, we end up with some prediction error. And our formal name for that prediction error is what we call a residual. And so a residual is just the difference between the actual y values and the predicted y values. So essentially the vertical distance between the data point and the line. So when you calculate your residual, there is a residual for every point on the line. And it's your observed minus your predicted y value, or y minus y hat value. The order of subtraction does make a difference because your values that are above the line here, your y value is bigger than the y hat value. So points above the line are going to have positive residuals, and then points below the line are going to have negative residuals because your y value is less than your y hat value. So you're taking something smaller minus something bigger. When you go to calculate your residuals, so y minus y hat, y is a point. So it's the y coordinate of your data point. To find y hat, you're going to take this x value, you're going to plug it into your y hat equation to get the y hat value that you're going to subtract. So y is the value from the ordered pair, y hat is the value that you get when you plug in that corresponding x to the equation. So we call our line of best fit the least squares regression line because what your line is doing is it's minimizing the sums of the squares of the residuals. So it's taking all of these vertical distances, so between the point and the line, and it's putting the regression line in such a place where it's making the average vertical distance as small as possible. And so you are never going to run into a situation where you have to place the line in the spot that's going to make those differences as small as possible. But that's just where the name comes from for least squares regression line. So your calculator or some computer software package is going to put the line in the right place for you. We can use the abbreviation LSRL for least squares regression line. It is a term that you will see, or an abbreviation that you will see in your textbook and on tests and quizzes, so you should recognize it. I would recommend using it as well, just because, again, writing out least squares regression line is quite a bit of extra writing. But when you see LSRL or regression line or linear regression, all of those terms are interchangeable for us at this point in time. So just kind of start to recognize those and know that they're really all equating to that equation for the line of best fit. So up to this point, we had calculated the equation for the least squares regression line using lin/reg on the calculator, and you're still going to be able to do that. So you can use technology. So this would just mean really your calculator or Statlet to come up with the equation for the least squares regression line. And you're going to use technology to come up with that equation if you have data lists. But sometimes the problem's not going to give you all of the X data and all of the Y data. Instead, you might be presented with the number summaries. So you might have means and standard deviations for both X and Y. In that case, you can come up with your equation for the least squares regression line using these two formulas here. So your slope is equal to the correlation times standard deviation of Y over standard deviation of X. Your y-intercept is equal to the mean of the y's minus the slope times the mean of the x's. Both of these formulas are in your formula sheet, so you do not need to memorize them. Just know that they're there. And just know that also the y-intercept formula is written in a different way on the formula sheet. It is an equivalent form here of what you're seeing. It's just that it's not solved for a. So if you subtract that bx bar to the other side, then you have what's in the green box here. You are only going to need to use these if you don't have the data, but number summaries are provided. So a problem might say the mean and standard deviation for list 1 are these values, mean and standard deviation for list 2 are these values, and the correlation is this, and then have you come up with the equation for the least squares regression line. One other thing that's noteworthy here is that because this is the formula for our y-intercept, your line will always pass through the point that's the mean of the x's and the mean of the y's. So here's your homework assignment for tonight. And then I do want to show you the formula packet quickly before you go off to work on that homework. So these are your formulas. Let me just make this a little bigger here, that you're provided on the AP exam and that you can use on tests and quizzes. So you see some of these that we've looked at before. You've got your mean formula, your standard deviation formula, but then right underneath there, you have your least squares regression line, y hat equals a plus bx. And then just to the right of it, you have the formula for your intercept. Again, it's just written in terms of y bar equals. So if you solve for a, you have y bar minus bx bar equals a. So you can use that for the y-intercept. And then your slope formula here, the correlation is times standard deviation of y over standard deviation of x. So you do not need to memorize those. They're there. Just make sure you know where they're located. And also, you do have to find the slope first. So it's kind of maybe thinking a little backwards, like this one maybe should be on top. So do slope first and then plug in to find your y-intercept.